Okay, good morning, everybody. So we're discussing the training and performance of the self-organizing map yesterday. So this is the map. It is where neurons are organized as a 2D array, typically. And then when you present an input, you see which is the neuron which is closest to the input, that is which has the highest response. And then you not only move the centroid of that neuron towards the input, but also move centroids of the neighbors of that winning neuron. So these neighbors constitute what is called a neighborhood. And when you do that, you'll end up with a map where nearby neurons respond to similar inputs. Okay, so because that is the property of the brain maps, and that is the property that the self-organized map tries to emulate. So we also discussed that there are these two phases of learning: the ordering phase and settling phase. In the ordering phase, the kings and the folds of the map are cleared up, right? And then in settling phase, the map simply tries to spread out over the entire input data set and completely represent it. So in this picture, you can see the first three pictures, right? Panels are constitute in the ordering phase, and our next two are in the settling phase. This is another example where a one-dimensional map is used to represent 2D data. So typically, the map is low-dimensional, as a 1D, 2D, and rarely 3D. Whereas the data can be n-dimensional. So you can think of the map as a mapping from so n dimensions to low dimensions. So usually ND to 2D. Okay, so it's a map onto lower dimensions. So therefore, you can use it for visualization. So if you have a high dimensional data set, and if you can map it onto 2 dimensions, right, you can see a picture of that high dimensional data set. Of course, there's a huge distortion involved, but still, it is an approximation, and it's like a map or a visual picture of the high dimensional data set. I'll show some examples of that. So this is a 3D data, right, where the variation is more in x and y dimensions, but in the z dimension, the variation is not much. So when you train the map on this data set, you see that the map is trying to capture the z data, but in terms of these little folds, but it's mapped, it's spread out more or less uniformly over the 2-dimensional surface. This is a more complicated map. The map is 2-dimensional, but the data is from 3D, and data comes from very strange geometry. Actually, it looks like a cactus, right? So the points in the data set fill this cactus, this 3D cactus, and a 2D map is trained on this data set. So see how it kind of takes the form of the 3D shape. The 2D is, imagine you have a cloth, right, on which you have done some grid pattern, and you are trying to now fold this cloth into so that it fits into the shape of some given shape, some 3D shape. So that's what the SOM is doing basically. So that's, you see that in this example. So again, another 2D example, but you can see the neuron locations, the centroid locations in the beginning, and how they evolve with training. So in the beginning, so the data comes from a unit from a square, right, between -1, 1 in both dimensions. So initially, centroids are like this. And since when you connect the centroid, so each centroid has neighbors, right? Because it's a 2D grid. So initially the centroids are all disordered, right? Then they're not nicely, they're not ordered like nearby centroids are close to each other. So once when you start training, see that map is like evolving gradually. You see that it's getting slowly unfolded in such a way that nearby centroids are. So there are, each centroid has positions in 2 spaces. One is in the map space, another is in the input space. Map space is low dimensional. In this case, it is 2D. So each centroid has a location of the given by the index ij, and the centroid also has a position in n dimension, which is the input space, and that corresponds to the centroid itself, which is a vector, right, in n dimensions. So nearby centroids in the grid space or the map space should have nearby nearby neurons in the map space should have nearby centroids in the input space. So that is the whole objective of the map. So you see that it's already tending in that direction. So there's still certain crumpling, right, or disorderly pattern in this part of the map. But otherwise, everywhere else, it's mostly unfolded. So this is still in the ordering phase. So now it has become clear all the kings are gone. It is now in the settling phase. Actually, yeah, it is from here onwards, whatever happened, mostly it's settling. So from 1000, maybe it will take another 1000 iterations to completely clear. After that, it's only settling. This is a final state of the map. So another example, you can see it in animation, right? So let me do that again. Initially, the centroids are some random locations. They are out in the middle of nowhere. The data set is not uniformly distributed. It has a bunch of clusters. So the map spreads out and fills all the data set. And you can also see that wherever there is data, there are more neurons in that part of the input space. And there are also some neurons kind of stuck out there in between. They're kind of like dead neurons. And this is inevitable because in the map, basically all the neurons have to move together, right? In the previous clustering algorithms, especially online k-means, each centroid moves independently, right? Whereas here, when a centroid moves, it drags along its neighbors along with it, and that centroid drags its neighbors, and so on. So they have some kind of a collective destiny. So because of that, you end up with these kinds of dead units. But anyway, the objective of the SOM is not just to cluster the input data set. It is also to come up with a more or less some kind of a continuous mapping of the input space onto the two-dimensional space of the grid. So you need those dead units out there in the middle of nowhere. This is an interesting study called Phonetic Keyboard. It was developed by Kohonen, a Finnish scientist, way back in, I guess, in the late 90s or late 80s or something like that. So basically, they have taken speech samples from Finnish, right, the phonemes of Finnish language, and they have trained a song on those samples. So then, so just like in the song, nearby neurons respond to similar inputs or similar stimuli. So you see that the phonemes are nicely mapped on this grid, and you can see similar phonemes sit next to each other in this map. So for example, U and V, right? But this is not the letter shape, obviously, it is a sound characteristic. Va and va, right? That is U. And pa and the or the, right? Anything else? Yeah, vowels are here. You see that A, O, E, O, U. Vowels seem to come to one side pretty much. There are not many vowels on the other side. So this happened automatically. I mean, it's not trained to segregate vowels and consonants or anything, right? But automatically, in fact, if you look at Indian languages, right, vowels are actually segregated like this: U, and so on. So aha, interestingly, is also a vowel in Indian languages, right? So you see that they're all segregated to one side of the map automatically, and then it starts with ka, right? And all the other consonants come later. And ra is some kind of a semi-vowel. It's neither a consonant nor a vowel, something in between, strictly speaking. Although it's in Indian languages, it is grouped under the consonant heading, but actually it's something in between. So interestingly, even the map puts it somewhere in between the consonants and vowels. So all these intuitive relationships among these entities, right, which are the phonemes in this case, are nicely brought out by the song. So this is another example of like that, mapping world poverty. So they've taken some, I think, 38 or 39 indices of quality of life from various countries and trained a SOM on that. I guess, so I guess the yellows are kind of wealthy nations and purples are somewhat poorer nations and so on and so forth. Okay, so you can see, where things, so you can see the gradations, especially you can see what are the border nations, which are not too poor, not too wealthy, and things like that. You can see all those shades of differences very nicely in this song. And also, since it is a two-dimensional map, right, it's a great way to visualize, because obviously you cannot visualize certain dimensional vectors, right? But you can visualize a 2D image, and also you can give some colors to make the map interesting. So this is an example of data visualization, which we have discussed in the early part of the course. So the same thing, if you show on a one map, it looks like this, but in a SOM, it looks like this. Now let us look at a couple of examples of SOM in biology. There are lots of examples, but I'll just take two representative papers. One of them is to represent what is called insulin resistance syndrome. These are shades of diabetes, right? How do you show that and visualize that in a SOM? So they've taken several variables: blood glucose level, insulin, serum insulin level, triglycerides, and so on and so forth. Okay, so then they have trained a SOM, and some of the classes they have are C1 is healthy controls, C4 is hypertensive and compensatory hyperinsulinemic subjects, C4B is insulin resistant, C2, C3 are like intermediate groups, are kind of borderline cases. So we just take this vector, all these parameters, and train the SOM. Now these are classes that you give after you train the SOM. You don't use the class information to train the SOM, because the SOM is basically an unsupervised learning method. That means you don't feed class information. So we look at the difference between supervised and unsupervised later on when we discuss supervised learning methods. So when you train that, it looks something like this. You see that C1, so the kind of the severity of the disease is indicated by the kind of the blackness of the color. So white is, oh sorry, no, it's the other way around. Yeah, so black is healthy and white is disease. So the healthy case are all here in the lower part of the map, lower and left part of the map. And as you go more and more towards kind of northeast of the map, you see you go more towards a disease condition. So C2 are borderline cases, so they are somewhere in between. So C1 is healthy, right? And C2 and C3 are both borderline. So disease conditions C4 and C4B, they're all here, right? So you can see how this particular subcategory of C4B, where it is situated with respect to the general diabetic condition of C4. Okay, so this is again a nice example of visualization. Now another such example is mapping gene expression data using SOMs to interpret gene expression data. So in this case, if we just take, so what they do is they take gene expression, how a gene is expressed over an entire cell cycle. Okay, and that they track about 800 genes, I think, right? And they track that towards over the entire yeast cell cycle, and then they try to map this on just to understand which genes are similar, which genes are expressed in a similar way, right, throughout the cell cycle, which genes are different, things like that. If you just train them on k-means, you just get an unorganized set of clusters, right? Whereas you won't see any this kind of a continuous variation and relationships among the genes. So they have taken a 5x6 array, right, of a SOM. SOM doesn't always have to be a square map; it can be a rectangular map also, size m by n. So they have done that, and they have taken 828 genes totally. They trained a 6x5 SOM. So that is, it's basically dividing the entire set of genes of 828 into 30 clusters. So you see that, so this picture, so each of these curves tells you how the gene expression level is changing throughout the entire cell cycle of whatever duration, right? And so you see that, so this graph is actually the mean of the expression pattern of all the genes which are clustered together under this neuron or this point in the map. So each of these is a neuron which represents a cluster. right? And so you can see that nearby neurons in this map uh, capture or represent genes with similar variation over the cell cycle. So look at this, both of them, in both these cases, there is a high expression in the middle of the cell cycle, and after that there's a fall, and toward end of cell cycle again there's increased expression. Similarly, in the last, if you look at these last four, right, there are two peaks in the expression somewhere in the first quarter or somewhere in kind of like the last quarter or second half, and you see the same pattern in all these four. But when you right here also you see something like similar, but again when you move away from there, there's a lot of difference. So you see that the differences are varying continuously, right? This is something that what is special about a song. And if you need this feature, a song would be a great asset. Okay, so yeah, it also picked cell cycle periodicity, and so genes in the same cluster typically peak during the same phase. So within the same cluster, so this graph shows average. So within the same cluster, the gene expression peaks at the same place. Not only that, nearby clusters also have genes which have the same pattern of peaking. So for example, 24, 28, 29 have genes that peak in late G4 phase, G1 phase. Right, so 24, 28, 29. So this, right, these three kind of cells, these three kind of neurons, right, have represent genes which have the same peaking pattern, expression pattern. So that's all about the self-organizing map. If you have any questions, I can take it, or I'll move on to the next topic. Where is my friend Kishan? He always asks some questions. Okay. So the next topic we'll cover is fuzzy logic and fuzzy clustering. So the first half of the course, I'm covering a whole lot of clustering techniques in kind of a sequence, so that when you understand one technique, that will lead you on to the next one. So that is because we have seen a lot of in the hierarchical clustering. At the end of it, we have seen this scale-based clustering, which involves this kind of a Gaussian calculations and all that. And then we also have seen an SOM, where again you use Gaussian to calculate the response of the neuron. So since we are in that flow, right, it will be nice to look at a slightly related kind of clustering technique, which is fuzzy clustering. Right? And then fuzzy clustering, then if you understand those equations, that can nicely lead you on to another kind of clustering, which is what is called expectation maximization. Okay, so well, I am trying to order these methods in such a way, in a fairly logical fashion, so when you understand one, you can understand the next one. So what is this fuzzy clustering? So to understand that, we should first understand what is fuzzy logic. So this term was introduced by Lotfi Zade. I think he was at UC Berkeley in 1965 in a paper written in 1965 on what is called fuzzy set theory. But apparently, it had its origins way back in 1920s, where these two people, Lukasiewicz and Tarski, they proposed something called infinite valued logic. Generally, a logical variable has two values, 0 or 1, true or false. But what if a variable has continuous values anywhere between 0 and 1? Then that will have infinite values. So I guess that is what these guys were doing. But fuzzy, I don't know, maybe it didn't become very popular. But when Zade proposed fuzzy logic, it became instant hit. There are a lot of applications and all that. So basically, in fuzzy logic, as opposed to traditional logic, you describe the truth of a phenomenon, right? Of something, of an object, right? In terms of a truth variable. In a classical description, truth is binary, right? It's either something is yes or no, or true or false. True means 1 and false is 0. And all the operations are done based on these binary variables. But real world truths are somewhere in between, right? They are what you can call fuzzy. They are vague. Okay, so somebody says, the sky is cloudy, right? How cloudy? And somebody says the room is too cold, shut off the AC. How cold is cold? I mean, for some people that's just right. Some people it's already very cold, right? It's relative. So there's a joke about this kind of a thing about there's like real world examples of how truth cannot be expressed as true or false, in binary terms. So apparently the one guy was kind of arrested for domestic violence. The judge asked him, "Can I take it that you have stopped, harassing your wife these days?" Right. So if he says yes, it means he was harassing his wife before. If he says no, he's still continuing to harass. So either way, he's in trouble. So that's just a joke about how 1-0 kind of an answers won't work in many real world situations. Okay, therefore we introduce, or in fuzzy logic we introduce something called a fuzzy variable, which quantifies the degree of truth. So that is the keyword. So in truth, there is as if there is a degree of truth. So for example, you want to define hotness. If you say hotness has a level or degree of 0.9, it's very hot. If it is 0.5, it is not that hot. Okay, so now this kind of, you might say, it sounds like probability, but there's a very important difference. Both have values between 0 and 1, both probability and fuzzy logic variables, right, have values between 0 and 1. But fuzzy logic uses degree of truth as a mathematical model of vagueness. So I want to specify the truth of something, but in a vague way, right? So it doesn't refer to the probability of occurrence of something. It's not like I'm tossing a coin and I want to know how many times I'll hit it head as opposed to tail. This is not the case. It's not a question of events. It is I can only express something vaguely, and how do I do that? In fact, in real world language, and that's how we talk. We don't. If somebody asks you your age, right? You don't say I'm like 20 years, 3 months, 12 days. I mean, you don't talk like this, right? You might just say 20. That's an approximate assistant. Similarly, if you say, let's say you have a new professor who has come to teach you something, and that guy is balding and all that, right? If somebody asks you how is your new professor, you may not say like, no, he seems to be 63 years old, 7 months. You say he's kind of oldish guy, right? Or you might say he's not old, but he's kind of old. I mean, obviously all these are vague qualifiers. These are not precise numerical qualifiers, ways of describing the quantity or the phenomenon. So that's how we talk in real world. Now the whole idea here is, can we make a logical framework out of that kind of description and make it rigorous, right? So for example, if you look at fuzzy variables for temperature, you can say it's cold, warm, or hot, but what is cold, what is warm? And giving precise boundaries for this is also not right, because then that destroys the whole spirit of fuzziness. If you say less than 0 is cold and 0 to 10 degrees is warm, then it's not fuzzy anymore. So how do you do this? Similarly for age, you say young or old, and so on and so forth. If you want further shades of it, right, at the edges or at the borders, you say somewhat young, rather old, and things like that. So how do you do that? Let's take this example. So the qualifiers like cold, warm, and hot obviously refer to temperature, but same time they don't refer to exact intervals of temperature. They refer to only approximate intervals of temperature. So how do you do that? You say, for example, that a temperature. Okay, let's say this is 0 degrees, just for convenience. Okay, so let us say this is some minus 3 degrees. Anything less than minus 3 is considered, let's say you consider as very cold. When it's cold, by no argument, you cannot, by no stretch of imagination, you can interpret it as warm. So this is pure cold, therefore it is cold to a degree of 1. Now, beyond that, now it is debatable. Some people might find it bearable, some people might find it cold, and so on. So then the degree of truth of coldness keeps going down as temperature increases. And let us say this is, I don't know, some 10 degrees centigrade. So 10 degrees centigrade, I don't know, maybe people feel generally warm, or maybe let's take it 20, right? It is clearly warm. So after 20, it is clearly warm, so warm of degree 1. But between this minus 3 and 20, it is warmish, right? Somewhere in between. So you have a continuously increasing quantity there. So now if you are asked the question, right, is it warm right now? That is, you give the temperature per value, and you ask, is it warm? So warm is a function of temperature, and you need to give a variable value, which is between 0 and 1. So that value is given by this warm function, which is the yellow line. Okay, so for about between 20 and let us say 40, I'm just saying, because 45 is considered like painful. So I'm just saying this is right 40. So 20 and 40, it is clearly warm, and it is the warm point value is 1, fuzzy variable value is 1. Less than 20 and up to minus 3, it is less between 0 and 1, it's neither 1 or 0. Similarly, greater than 40 and up to let us say 45 or 50, right, it is again between 0 and 1 and moving towards hot. So the yellow curve here or yellow graph here is the warm function. Similarly, the blue graph here is the cold function, and the red graph here is the hot function. Now, so for if you give a temperature for a temperature value, right, you can give three functions: hot, warm, or cold. At temperature 50 degrees, if you plug it into into cold function, it will be 0. I mean, it's basically it's not cold at all, right? And also, just like probabilities, if you add up all these functions, cold plus warm plus hot, for any given temperature, right, it gives you 1. That's how they are designed. Because a temperature at a given temperature, it's either cold or warm or hot, and it should be one of them. The only thing is, it is one of them to different extents. It's not like it's not like if it is hot, it is not warm. Something can be slightly warm and slightly hot. Something can be slightly cold and slightly warm. So the temperature can belong to multiple sets. If you think of cold, warm, and hot as 3 sets, and put your temperatures in these 3 sets. Some temperatures belong to only cold and not warm, or only warm and not hot, like these intervals. And some temperatures belong to slightly too cold and slightly too warm. So here you have a new kind of set theory, where the entries belong to a given set to a given degree, right? So the temperature here T belongs to C, the cold and warm to different extents. So if it is here, so let us say this is 0.5. So this temperature T, let me call this some T1. So T1 belongs to cold with a degree of 0.5 and belongs to warm also to a degree of 0.5, because it's a borderline case. It belongs to both sets with a kind of a partial degree. So now this is the kind of a description that you use in fuzzy set theory. In fuzzy set theory, a set has a bunch of members, right, or elements. Now, normally in a given set, the element is completely present in the set. There's nothing like to what extent, to what degree the element is present inside the set. But that's classical sets. In fuzzy sets, an element belongs to a given set to a given degree, right? So, for example, if an element belongs to 2 sets, like this, 0.5 and 0.5, it's some kind of a borderline member or member element. So, people also have defined fuzzy logic operators, like you have and or and not logical operators in classical logic. In fuzzy logic, that becomes min. So, for example, if you look at AND gate or AND logic, so 0, 0 is 0. So x1, x2 are the inputs and y is the output. So this is AND gate. 0, 1 is 0, 1, 0 is 0, and only when both or x1 and x2 are both 1, y is 1. So it's some kind of product, right? So if you see, there's a mathematical way to calculate the output from the 2 inputs. So I'll use the operation min, right? If I take the min of the 2 and set it equal to the output, I mean, you get the same result, right? Right. So in all these 3 cases, min is 0, so here it is 0. In this case, min is 1, so here it is 1. So similarly, if you take the OR gate, again you take x1, x2, and y, you have 0, 0, 0, 0, 1, 1, 101 and 111. So in this case, it is a max because in all these three cases, the max is 1, so output is 1. In this case, the max is 0, output is 0. So because in fuzzy logic, the truth variables are the fuzzy variables are between 0 and 1. They're not exactly equal to 0, exactly equal to 1. Not always. So therefore, to generalize that, right, they have, because this takes the AND case as a special case. So min of x comma y is a fuzzy AND operation, and max of x comma y is the fuzzy OR operation, and 1 minus x is a fuzzy NOT operation. Because if something is cold to a degree of 0.2, right, it is hot to the degree of 0.8, okay, because that's the complement. That is the logic behind this. So this very soon after it was proposed in the 65, so a lot of applications, particularly Japanese manufacturers, have taken up fuzzy logic in a big way and have incorporated them in a lot of devices. So, for example, washing machines and subway train control and things like that. Even recognition of handwritten symbols in Sony pocket computers. Flight 8 for helicopters and controlling subway systems. Fuel consumption in automobiles, fuel injection, uh, and washing machines, motor control for vacuum cleaners, prediction system for early recognition of earthquakes in Japan again. So the thing is, this is because what is happening is fuzzy logic lets you convert your intuitive descriptions, which are vague and very qualitative, into quantitative operations or procedures. So it was a big thing at that time, but now with all the deep networks and AI going on, we don't. These techniques are too preliminary. Okay, but it's good to know that all these techniques exist, and also what we are interested in is how do you extend all this to uh, clustering, right? So let us come to fuzzy clustering. So for that, I'll just use some kind of board work on the slides. Okay, so in k-means clustering, right? If you have a data point, here is a cluster, and here is another cluster. A given data point completely belongs to a given cluster. But there's nothing like, right? Even if you have a data point on the border, it is nothing like this belongs to this cluster a little bit and this cluster a little bit and all that. So that kind of situation doesn't exist, right? Where it's completely partitional algorithm. Whereas in fuzzy clustering, right? Let us say I have two clusters, right, with some data points. This point is close to the border of two clusters. So I can say that it belongs to this cluster with a weightage of, I don't know, 0.8 and belongs to this cluster with a weightage of 0.2. That's a kind of logic, that's the spirit of fuzzy logic, right? So we can do that. Now, point is, and maybe if I take a point here, that's completely inside this cluster 1, so I can give it a membership to cluster 1 of state 1, and therefore its membership to cluster 2 will be 0. Because the idea is just like in probability, a data point should belong to one cluster or other, right? So each data point now will have some membership to every cluster, and the sum of all the memberships should equal to 1 for a given data point. So to basically, if you look at clustering, it's a mapping between a data point xj and a cluster ci. That is what we achieve in clustering. So now, unlike in k-means, in fuzzy clustering, a data point xj can belong to each cluster C1, C2, Ci, Ck, the totally take K clusters to different extents, so to different degrees, right? So that is defined by certain weighting parameter called Wij. Okay, so now earlier the objective of clustering is to work out this mapping between Xj and Ci, right? The ith j data point and the ith cluster. So that since in fuzzy clustering, every data point can in principle belong to every cluster, but at different weightage levels. The objective of clustering is now to find out what is Wij. Okay, so how do we proceed with this? So first of all, should we apply some constraints to Wij? Because Wij cannot take any value, right, that it pleases. There must be some constraints. And how do you go about finding that? Let's take a simple example, right? Let's take again the same. I have two data sets and I have 7 points totally in two clusters, C1 and C2. So if we take the traditional method, right, how do we express the belongingness of data points to clusters? So I'll draw a matrix like this. I'll draw a matrix like this, and on the rows, I indicate the data points. And in the columns, I indicate the clusters. Call this C1 and C2. So now this mapping between the data points, the J's, and the clusters, which is the I's, right, can be given like this. Since data point 1 belongs to C1, I'll give that, so I'll define a variable 1 here for C1. And it doesn't belong to C2, so I'll call this 0. Okay, so 2 also belongs to C1, but doesn't belong to Z2, 0. 3 also belongs to C1, doesn't belong to C2. Now, this is 4, number 4, so I'll call this 1, 2, 3, 4, 5, 6, 7. So 4, 5, 6, 7 belong to C2. So okay, so this matrix now is basically the same thing, the same mapping I'm defining as a matrix. Okay, so now from this we'll try to go to this more general case of Wij. So first of all, so now in fuzzy logic, what can happen is data point 1 can belong to C1 to a degree of 0.9 and C2 to a degree of 0.1 and things like that. Okay, so that's how the matrix will look like. So we'll see how to compute it and all that in a minute. But what are the conditions do you think are applicable, right, to this kind of a W matrix? I'll call this Wij. What conditions do we have to place on W for it to be a valid fuzzy membership matrix for this clustering? Anybody? Is anybody listening?
The sum across all I should be 1.
Yeah, for a given J, very good. Sum across all I's. I goes from 1 to K. K is the total number of clusters. That should be equal to 1. So what that says is a given point has to belong partially to, right, to all the clusters. So its total membership over all the clusters should be equal to 1. In this case, is obviously true because when every row you sum the elements in the row, that they equal to 1. Basically, that says that data point belongs to that cluster, only one cluster. There's one more condition, right? What is the meaning of this other summation, Wij over J, where J goes from 1 to capital N. N is the number of, so K is number of clusters, N is number of data points. So for a given J, right, if I take this summation, what is the meaning of this? In this case, what is the meaning of this? So sum over the entire column. Here, what is the number here? If I sum over the entire column for C1.
Number of points in that particular
Yeah,
cluster.
here it is 3 and here it is 4. So this is the number of points in ith cluster. Whereas when W becomes a fuzzy matrix, right, the number of points is not the exact term. We'll think of something like so sigma Wij, j equal to 1 to n is something like mass of ith cluster, because you're not talking about like discrete particles or something. Earlier points were like discrete particles. So here also discrete particles, but they can be split. They can belong to different clusters to different extents. So you can just talk about some kind of a mass of the ith cluster. Okay, so with these concepts now let us proceed. Let us see how we can construct this. Now, how do we define sum squared error? Because that was starting point of all, K-means clustering. K-means clustering, you had a sum squared error. So in K-means, SSE was equal to I goes from 1 to K, J goes to 1 to N, right? This where Xj Mi, I'll use slightly different notation. Okay, you know this notation, right? Mi of J is centroid closest to Xj. Because in textbooks, I've noticed that they just say Mi, but they don't add this condition. They just say it verbally in text, but that's somewhat misleading. Yeah, right, because you're not taking distance from every data point to every centroid. You're only looking at the nearest neighbor. So yeah, so this is a kind of a cost function that we use. What will be the corresponding cost function, right? For okay, no. So suppose I don't want to put this condition. I find it's awkward. Ij, I of j and all that. I just want to use the complete summation. So I equal to 1 to k, j equal to 1 to n. Okay, I just want to say this. Right, all to all. Obviously, this is not correct. Can you introduce something here? I'll have to have some space here. Can you introduce something here so that this expression will be correct? This expression will be identical to this expression. Something that says that, so even if you compute all possible distance values from every xj to every mi, in this expression, this summation only consider the correct values. That is, if you look at this table gives you all possible combinations between data points and the clusters, right? But the only allotments that are valid, that are actually present, are this, and this, right? So making use of this matrix, the presence of this kind of matrix, right, which intrinsically encodes all the mappings between data points and clusters. Can you change this expression like this so that the expression will become identical to this expression?
Minimum?
No. So thing is, for example, dist of x. So let's say x11 and x21. This is x11, right? Okay. Dist x1. So this point will correspond to dist x1 m1. This is dist x1 m2, right? Now, if I just take this full summation, take this full summation, I'll get dist x1 m1, dist x1 m2, both, right? Whereas I don't want both. I want to make sure that this term is set to 0, because I need to consider the distance square of, if I'm looking at data points, data point is already allocated to cluster 1. I've looked at distance square of data point 1 to centroid corresponding to C1. Okay, I shouldn't consider this. So whereas in this expression, the way it is written right now, it considers it considers all the entries in this array. Whereas we should not do that. We should only consider the entries that correspond to the actual mappings of data points and clusters. Right? So how do I change this expression? So that, whereas this here it is taken care of. Here, although we have double loop, you see that the i's that we consider are only the ones which correspond to j. Right? Okay, so let me just put wij here. You see what's happening? Okay, let me expand it out a little bit. Let's say for k equal to 1, I'll have this square. If I just take this expression, x1 m1 plus this square x1, m2, then for k equal to 2, I have this square, k, this is, for j equal to 1, j equal to 2, okay, this is x2, m1, so if I just take, without this wij term, if I just take this expression and keep computing it, you will get terms like this. But what I'm trying to say is, x1 to m1 distance square, that is correct. It should be there because x1 belongs to m1. But x1 to m2 distance square should not be considered because x1 does not belong to m2, to cluster 2, right? So similarly, x2 also belongs to m1 to cluster 1. So in the SSE, I will consider distance square as to x2 to m1. But x2 does not belong to m2, so I should not consider this term. So I have to set this and this to 0, but I need to include this and this. So what I am doing here is, if I include wij as a factor, this wij acts like a flag, right, which will make sure that only the corresponding terms are permitted and the wrong ones are all set to 0. So because if I insert wij here is 1, so I get 1 times this. Wij here is 0, so I get 0 times this. Here also it is 0. Here it is 1. So like that, it will, by application of this array here, this matrix here, and if you take full summation, right, it will automatically make sure that only the corresponding distance squares are considered. The rest are simply reset. This is clear? Because this, I'm trying to reformulate the SSC in new terms in such a way that this will automatically lead us on to the SSC for the fuzzy clustering. So this kind of a matrix formulation of the mapping between data points and clusters, that is very important to make sense out of fuzzy clustering. That's right. Any questions? Otherwise, we'll stop here. I think otherwise, because a lot of theory left and to discuss about fuzzy clustering. So we'll do it in the next class.